I'm happy to be here and to have given a lecture on low-dose effects of ionizing radiation. And I would like to make the following statement. All agree that high values of absorbed dose of ionizing radiation may be harmful, and they cause cancer. After acute or chronic doses below about 150 millisievert, the incidence of cancer did not rise significantly above the control values. The epidemiological failure to observe cancer after these low doses is due mainly to statistical constraints, since radiogenic cancer is very rare and non-radiogenic cancer in the industrialized countries is very frequent. Another reason may be that low doses do not cause cancer. The epidemiological dilemma asks for experimental observations in molecules, cells, tissues, and the whole organism, and feeding the data into mathematical modeling of cancer development. The traditional model most widely used conforms to the so-called linear no-threshold hypothesis, according to which any amount of radiation, however small, may be potentially carcinogenic, that may cause cancer or increase the risk of cancer. What was a good intention to protect people from overexposure to ionizing radiation has turned into a widespread radiation phobia. The plausibility of the linear no-threshold hypothesis derived from two assumptions. One, the initial damage to the genetic material, the DNA, from radiation exposure rises linearly proportionally to the absorbed dose. Second, certain initial DNA damage amplified and propagated in the organism may cause cancer incidence in proportion again to dose. However, more recent investigated data show that the second assumption is not correct and does not conform to the biological experimental data. The more recent biological experimental data with low doses show the living organisms have in all three types of defenses of barriers, a physical barrier and two metabolic barriers against radiation damage and its propagation from molecules where the initial perturbation occurs to cells where bystander effects and genomic instability may arise, to tissue organs where cancer clones may develop, and eventually the whole organism may succumb to metastases through multi-organ failure. These cascades of defenses at each organizational level of the body towards higher levels do not operate in proportion to the degree of perturbation, but in a deterministic manner. This means a perturbation needs to be overcome and needs to overcome a certain resistance in the system for the damage to occur at a given level of the organization and then to propagate to the next higher level. The physical barriers function through inherent elemental redundancy and elemental masses, and each level deterministically shows that there's a certain threshold below which there is no damage. The metabolic barriers are controlled genetically, and they may vary between individuals. These barriers include the following components: scavenging of toxins, especially of reactive oxygen species. Secondly, repair of molecular damage, especially that to DNA. And thirdly, removal of damage by cell death, apoptosis, for example, or cell senescence, or at the at the tissue level by immune responses towards damaged cells. The first type of these two metabolic barriers acts on short term, after perturbating impact has occurred, such as energy deposition events of radiation, which are to be seen as a toxin at that level. The second type of metabolic pairs involve upregulation of components seen in the first type. These functionally induced components show up with a delay, and they may last for months or even beyond a year. They conform in part to stress responses, also called adaptive protections. Most adaptive protections have their maximal probability at about 100 millisievert, and they disappear with increasing doses. Adaptive protections following low-dose radiation operate not only against renewed radiation, as often stated, but also against perturbation from non-radiogenic sources, so spontaneous cancer, and these arise mostly from a series of metabolic toxins, such as reactive oxygen species, which are constantly produced and abundantly produced in all living cells. By far the largest fraction of cancer incidence in the industrialized world is due to non-radiogenic toxins, like metabolic toxins. Therefore, the probability of clinical cancer after low-dose irradiation appears as the difference between the probabilities of induced cancer that may be calculated on the basis of the linear no-threshold hypothesis and of prevented cancer due to the action of the adaptive protection against non-radiogenic cancer. Experimental evidence suggests that at doses below about 100 millisievert, the two probabilities, that of induced cancer and prevented cancer, balance each other equally, or even show the probability of prevention to outweigh the induction, resulting in hormesis, with clinical trials perhaps on the horizon. In the face of these more recent developments, it is suggested that one replaces the linear no-threshold hypothesis by a novel approach that acknowledges both those effects, namely that of damage and of damage prevention, and allows a consensus to deal with the limits of radiation exposure and arrives at optimal radiation protection with the option of clinical application of low doses based on the individual genome profile. Thank you.